Okay, on to question 51. In the diagram below, a student compresses a spring with a pop-up toy. If the spring constant is 340 newtons per meter, how much energy is being stored? 1/2 kx squared is your energy, PE sub S. So 1/2 times the spring constant, 340 newtons per meter, times x is 0.02 squared. Don't forget the square. Let's see, I can't do this one as easily in my mind. 340 times 0.02 times 0.02 squared equals 9 divided by 2 is a half, so 0.068 joules. There we go. Diagram shows an apple attached to a branch above a spring. The apple falls and hits the spring. What a coincidence that someone put an apple right above a spring, or put a spring right below the apple. Okay, compresses it from the rear position. It says if all the gravitational potential energy is transformed to the spring when it's compressed, what is the spring constant of the spring? So this is a little tricky in that we're dealing with multiple forms of energy. You have GPE at the top, we have potential energy at the bottom in the spring, and in the middle there's kinetic. So gravitational potential becomes kinetic as it moves, and then when it hits the spring it slows down, eventually comes to a stop. So in theory, all the energy stored as gravitational potential energy becomes spring potential energy. So it's saying, what is the spring constant? Well, we know that the PE is going to be 1/2 kx squared, and we don't know what k is, but we know what x is because it tells you how much it's compressed, 0.1 meter squared. So that is 1/2 kx squared. Now we have to set that equal to something, and we're going to set that equal to the gravitational potential energy. So the gravitational potential energy becomes spring energy. So if the gravitational potential energy is mgh, 0.1 kilogram is the mass, g is 9.8 meters per second squared, and h is 2 meters. So I realize I'm solving this without units. I wish there was more space. 0.1 times 9.8 times 2 mgh is 1.96 joules of energy. So we know that there's 1.96, about 2 joules of energy stored, that as it falls becomes 2 joules of kinetic energy, that becomes 2 joules of spring energy. So 2 joules equals 1/2 kx squared, or 1.96 equals 1/2 k times 0.1 squared. So we're going to solve for k. Let's multiply that by 2, and let's divide it by 0.1 squared. So that gets k is equal to 392 joules. They round up to 400. I'm sorry, newtons per meter squared. Get the right. Newtons per meter. Get the right unit in there. 4. Yeah, 4 basically times 10 times 10 is about 400. Okay, perfect. The spring in a toy car is wound by pushing the car backwards with a force of 15 newtons through a distance of 1/2 meter. How much elastic potential energy is stored in the car's spring? So we know that the equation for elastic potential energy is 1/2 kx squared, but we don't know when, well, we know the x, right? We don't know the spring constant. F kx. So, well, questions like this get a little tricky because you can do like a force times distance, right? 15 times 0.5, but you could also try to solve for x, and you could do 15 newtons equals k times the distance that you do, 0.5. And if you do those, you might end up getting slightly different answers. So let's talk about why in just 1 second. Okay, so I got some scrap paper to do this with. So let's think about this. There's two ways to think about it. The work that you do, which is a force times the distance, is going to be equal to the amount of energy you add to something. So it says you're using 15 newtons of average force. I want to include the word average there. Times the distance of a half meter gets you 7.5 joules. So according to this, that one way, work is equal to 7.5 joules. Now, we also know that the spring constant can be found by saying force equals K times X. So this says you use an average force of 15 newtons. That, in theory, would be a spring constant of K times the distance of 0.5 meters. So you get K, you solve for K, you end up getting 30 newtons per meter. And using that 30 newtons per meter, you might say potential energy is equal to 1/2 kx squared, which is equal to 1/2 times 30 newtons per meter times x squared, 0.5 meters squared. And if you do the math, you get 30 divided by 8, which is 3.75 joules. Two answers giving us two different results. That says the work is 7.5 joules. This says that the energy is 3.75, but in theory they should be the same. So why aren't they, and what's the correct answer? Well, you might do this and just say 3.75 isn't here, so it's probably the 7.5, and that would be correct, but that's just by process of elimination rather than answering it because we know the right result. So here's the important thing to realize. As you stretch a spring, the force changes. So when it's not stretched, the force is equal to 0. When it's fully stretched, you get a bigger force. Let's call that the total force, F total. Well, this is saying that you're pushing with an average force. So you start at 0, you end at a final. So the average would be when it's actually only half stretched. Meaning the average is going to be when you're going to have 50 newtons of force when it's not stretched 0.5 meters, but when it's actually stretched at 0.25 meters. So that way you could change your result to find a different spring constant. So if you did that, you said that the force is at 0.5 meters, or if you said, hey, if here the force is 15 newtons, that's your average, and the average is in the middle, then your final force has got to be 30 newtons. So you could instead cross this out and say, oops, when it's stretched a half meter, it's not using the average force, it's using the final force. You end up getting a spring constant of not 30, but 60 newtons per meter. And if you put 60 in here, you want to find the energy when it's stretched to the max, to the 0.5 meters, and the spring constant's actually 60, then you get a potential energy of 7.5 joules. So I know this is confusing to you. The answer should be 7.5 joules right there. But you can get it simply by saying, hey, 15 newtons times a half meter. And the reason that this works is that, and this is a little bit of a cheat, right? But your force changes over time. So you're doing a little bit less work at the beginning when the force is less than 15. You're doing more work at the end when the force is greater than 15. But ultimately, you're averaging out. Normally, a force times distance function might look a little bit like this. Force times distance, and your work is the area of it. Well, what we're actually saying here is it's a little different than that. Force times distance is going to look like that rather than like this. But the area of the big triangle ends up equaling the same thing. That makes sense. So this actually, force times distance, actually does work if you use an average force, which I don't think is in here. I don't think that's on the reference table. But yeah, it doesn't say average force in here. It just says force times distance. Okay, complicated one there. A catapult with a spring constant of 1 times 10 to the 4th newtons is required to launch an airplane from the deck of a carrier. The displacement's 0.5 meters from equilibrium. The energy acquired during the takeoff is, okay. Energy is 1/2 kx squared. K is 1 times 10 to the 4th. So that's 10,000. 10,000 K 0.5 meters squared. So 0.5 times 1,000 times 0.5 squared should get us 1/8 of 1,000, 125. That's going to probably round up to 130. What? So what is not going right here? Because this doesn't answer. I think I put one too few zeros in there. 1250, yeah, okay. So if you get 1250, it's going to round up to 1300 right there. So answer A. A ball is dropped vertically from a height of 1 meter above the floor, and it bounces back to a height of 0.8 meters. Mechanical energy lost by the ball is. Okay, so let's say it starts with a certain amount of potential energy, which is equal to mgh. So 0.1 kilogram times 9.8 meters per second squared times the height of 1 gets us 0.98 joules. Now it ends with a certain amount of potential energy, PE equals 0.1 times 9.8 mass times G times the new height of 0.8. So let's do this. 9.8 times 0.1 times 0.8 gets us 0.784 joules. So if you subtract the two, you should get the energy that is lost by the ball as it bounces. That energy doesn't just evaporate, it becomes probably internal energy. As the ball heats up, the molecules start moving in the ball, and the molecules start moving a little more quickly in the table or the floor, whichever it hits the floor, it looks like. So let's see, 0.98 minus 0.784. Subtract the 2 gets us 0.196, which is going to round up to 0.2 joules. Okay, a pendulum in 3 positions, A, B, and C. No friction, nice to know. So it's a perfect pendulum. In theory, it should swing back and forth to the same height every single time if energy is conserved, and will keep going to the same height. Which statement is true? The PE at A equals the KE at C. The speed at A equals the speed at B. So that's clearly not true, because at point A, the velocity is 0, and here the velocity is fast. So that's not right. The potential energy at B equals the potential energy at A. That would imply that they are the same height, just like potential at B equals the potential at C. So that they're not the same height. That's not right. Potential energy at A equals the potential energy at potential energy at A equals the kinetic energy at B, and the first one says the potential energy at A equals the kinetic energy at C. So it's got to be one of those two. Let's think about it. The potential energy at A. Okay, so let's A. Potential energy at A equals the kinetic energy at C. Well, it's stopped at both points A and C. So at point C, the KE equals 0. So that's clearly not true. So you can't have potential energy at A equals the potential energy at C. The kinetic at A equals the kinetic at C, which is 0, but it's not going to be potential there. So this is saying the potential at A equals the kinetic energy at B, which has got to be true. Okay, so let's think about this. I'm not sure I love the way this question is written, honestly. But basically this is saying whatever potential energy is at A is going to be converted into kinetic energy. And it's got to be answer D. Having said that, sometimes it's a little bit wonky. So let's say that the potential energy is, because the total is going to be the same. Let me write up an example for a second. Okay. So I did this. I don't like this question. Let me tell you why. Let's say at point A, the potential energy is 20 joules and the kinetic 0, because it's not moving, right? So that means at point C, the potential energy is 20 joules and the kinetic is 0. So what does that mean about point B right here? Well, B is probably above the ground, so you could easily define its potential energy as not 0. So what if we said that its potential energy was 5 joules? Well, if the total here is 20, the total here is 20, the total here should be 20 also. So this should be 15 joules. And this is arbitrary because we don't know, we haven't measured heights, for example. But if that's the case, the potential energy here of 20 doesn't equal the kinetic energy of 15. So I really quite dislike this question. But having said that, it's interesting to think about. So this works. Answer D is the correct answer because none of the other ones make sense. But it only works if we define point B as having a potential energy of 0. So if we say that this is height 0, then you can say, hey, then all this potential energy here has got to be converted into kinetic energy. So it's not like 15 being converted to 15, it's all 20 joules of potential energy is converted to 20 joules of kinetic energy here. So then the math works out. So if it had said something as defined, or the change in potential energy equals the change in kinetic energy, that would have been better, as opposed to just saying the potential energy equals the potential energy. Okay. Let's go to a roller coaster question. Here we go. Okay. Car at point A, it carries 75 kilograms, and is 20 meters above the ground. Calculate the GPE relative to the ground. See, they say relative to the ground. That's nice. At point A, show all work. Okay, so GPE, gravitational potential energy, is mgh of the car and the passenger. So let's just say, I'm going to write an equation here. PE equals mgh. Mass. So let's say the total mass, m total, is 250 plus 75. So 325 kilograms. So the mass is 325 kilograms. There's my equation. G is 9.8 meters per second squared. There's my substitution with units. And the height at point A is 20 meters. Put all those in. My calculator, 325 times 9.8 times 20 is equal to 63700 joules. You could do different units. You could do kilogram meters squared per second squared. That's fine, but we know it's energy, so it's got to be joules. Equation, substitution with units, answer. Okay. Calculate the speed at point B. Show all work, including equation and substitution with units. So, point B. Well, let's assume that this is frictionless. It probably says that right there. Yep. Okay. Now, a lot of times that's tricky unless you realize that energy is completely conserved because we're dealing with an ideal mechanical system. So your potential energy should equal your kinetic energy. Technically, your change in potential equals your change in kinetic. But it's initially at rest, right? So that's important to keep in mind. So the total energy there is 63,700 plus 0. So E total is going to be 63,700, which means down here, your total energy is 63,700, except your PE is equal to 0. So if your PE equals 0, that means 0 plus something equals 63,700. So that something is your kinetic energy. So that means your kinetic energy at the bottom is 63,700. 63,700. So let's write the equation. KE equals 1/2 mv squared. It's a square there. 63,700 joules equals 1/2 times the mass, which we said was 325 kilograms, times your velocity squared. Now, we're going to solve for v squared. So I've got my equation, my substitution with units. I can now solve v squared is going to equal 63,700 times 2 divided by 325, 392. I don't need units in there, I just need units in the final answer. So v is going to equal the square root of that. You can take the square root of both sides. And we take the square root. And so the answer should be 19.8 meters per second. I need units on the answer as well. There we go. Two carts. After the collision, the carts lock together and move together. Collision, interesting. So this actually has something to do with momentum, right? Which is not in this unit, but there's probably a reason I included this in here. So calculate the speed of the combined carts after the collision. So P total before equals P total after. So initial total is 1,000 kilograms times 6 meters per second plus 5,000 kilograms times 0 meters per second. So this has a 6,000 kilogram meters per second, whereas this one has 0. 6,000 plus 0 is just 6,000. So my total momentum is 6,000. Now, once I know that, they lock together, right? So they are now having a P after, and the total mass is 1,000 plus 6,000, 5,000, so 6,000. So we can say P after equals m mass, the total mass, times the velocity, because both carts are moving at the same velocity. So you get 6,000 kilogram meters per second equals a total mass of 6,000 kilograms times v. Solve for v. V equals 1 meter per second. So it's slowed down considerably as a combined. What is the kinetic energy of the combined carts? Well, the KE is 1/2 mass v squared. The mass is 6,000 kilograms. Velocity is 1 meter per second squared. 1/2 times 6,000 is 3,000 times 1 times 1. It should be 3,000 joules. How does the kinetic energy of the combined carts compare to the kinetic energy of the carts before? So if that's the total, KE before is going to equal 1/2 times 1,000 times 6 meters per second squared plus 1/2 times 5,000 times 0 meters per second squared. So that just becomes 0. So let's do the math for that. 0.5 times 1,000 times 36 equals 18,000 joules. So before it was 18,000 joules, after it was 3,000 joules, so it lost a lot of energy. So it's a lot lower afterwards. So there's a lot of internal energy that went into this collision. It would be a problem, most likely, if it gained energy. You wouldn't expect it to gain energy, you'd expect it to lose energy. That lost energy becomes internal energy. Thank you very much. Okay, on to 61. A driver of a car makes an emergency stop. The wheels lock, the car skids to a stop, probably because of friction. The wheels are 16 meters long, and the car's mass is blah, blah, blah. Okay, a lot of information there. Let's just look at the question. Calculate the magnitude of the frictional force applied to the car. So we're going back a little bit. Rubber tires on dry asphalt. So that's a sign that we might actually need to look up coefficients of friction here. Rubber tires on dry asphalt. It's moving, so it's going to be kinetic. So mu is going to be 0.67 right there. No units to that. So frictional force is going to be mu times the normal force. But the normal force is going to be equal and opposite to the car's weight. So 0.67 times the mass, 1,200 kilograms, times 9.8 meters per second squared. So that's weight times the coefficient of friction. Turn this on. 0.67 times 1200 times 9.8. That's not right. 0.67 times 1200. Sometimes you punch things into the calculator, you miss a number. There we go. 7879 newtons. Okay, what is the work done by the frictional force in stopping the car? So the work is equal to force times distance. We know the force, 7879 newtons, times a distance of 16 meters. Multiply that by 16, and we get a nice big number. 126. I'm just going to round. About 126,000 joules. Okay, if energy is conserved, that means if all the energy, this 126,000 joules, was kinetic energy, let's figure out how fast it was going. So we would set that equal to the kinetic energy. So we can say the KE, which is 126,000 joules, equals 1/2 times the mass times the velocity squared. So the mass is 1,200 kilograms, and v squared, and we're going to solve for v. So multiply that by 2, divided by 1,200. So v squared is going to equal 210. So v is the square root of 210, which equals 14.5 meters per second. Your answer might be a little bit different depending on how you rounded. Okay, a proton starts from rest and gains a bunch of kinetic energy as it accelerates between points. What's the final speed of the proton? So I think we're going to be using a conservation of energy thing here. So the energy of a proton, kinetic energy, is 1/2 mv squared. So let's say 8.35 times 10 to the negative 14th joules equals 1/2 mv squared, and solve for v. Well, we also need the mass of a proton, so let's look on the rest mass of the proton on the reference table. 1.67 times 10 to the negative 27th v times v squared. So v is going to be the square root of, let's see, 8.35. I'm going to do the second function, e thing here, negative 14. Multiply that by 2. Divide it by 1.67 e negative 27. You put parentheses in if you're not sure what you're doing. I didn't do it because I know that the e doesn't make me do it, but so v is 1 times 10 to the 14th, v squared is. So take the square root of that, and it should be 1 times 10 to the 7th. There we go, which is answer B. Okay. We got 3 points. A mass is hung from a spring. It's raised in its equilibrium point is B. And it's bouncing back and forth between A and C. What point is the mass located where the kinetic energy of the system is at its maximum? Well, at the very top, the KE should be 0 because it's at rest. And at the very bottom, it should be 0 because it's at rest. It's moving quickest in the middle, B, so that would be point B. When it's moving quickest, the most velocity, then kinetic energy is maximum. Okay, at which point is it located when the gravitational potential energy is at max? So it's going to be the highest point. The highest point is going to be answer A. Okay, at which position is it located when the elastic potential energy is at max? So elastic or spring potential energy is 1/2 kx squared. So let's think about this. I mean, it's the elastic potential energy is going to be max when it's most when x is biggest. Now, I think what they're going for is, I assume, answer C. If you're comparing it to the equilibrium point, then A and B should have the same amount of stretch in theory. But, well, no, this is not a compression. I'm sorry. This is just all pure elongation. So it's most elongated at point C. Just want to make sure I'm getting this right. Okay. Because this is, the equilibrium point is different than where it has 0, because it's got a mass hanging from it. Greatest elongations at point C. Okay. A box on a big thing. Lots of questions. It says on the diagram, so, I mean, you read this, you don't even need to know half the stuff there. Construct a vector to represent the weight of the box. Use a metric ruler and a scale of 1 centimeter. 1 centimeter equals 40 newtons. So if the box is 160 newtons, we want to change that to centimeters, where 1 centimeter is 40 newtons. So 160 divided by 40, and you cancel out the units, right? You should get 4 centimeters. So let's draw this. Gravity points straight down, right? I'm going to start at 20, so 21, 22, 23, 24. Boom. Vector has an arrowhead, points down. The tip of the arrow is 4 centimeters below B. Okay, calculate the amount of work done in moving the box from the bottom to the top of the plane. Show all work. Well, work is force times distance. The force is the weight of the box. mg, which in this case is 160 newtons, is the weight. It's given in newtons. And the distance we care about is purely horizontal distance. I'm guessing, let's see. So it's on a 10-meter long frictionless plane. Okay, good, frictionless. That's the word I was looking for. Okay, and so if it's frictionless, we're just, the only thing we're doing work against is gravity. So we only really care about this side, the triangle. So this side of the triangle, if the hypotenuse is 10, this is opposite the angle. So that would be 10 meters times the sine of 30 degrees, which is going to be 5 meters. So the distance is 5 meters. 160 times 5 gets us 800 joules. Equation, substitution with units, answer with units. Okay. A block of mass m starts from rest at h on a frictionless incline. It slides down, forms mechanical energy possessed by the system when it's in position A and in position B. So at A, starting at rest, so it has no kinetic energy. So at A, it's going to be have gravitational potential energy, P sub G, right? It doesn't have kinetic energy. At position B, it's going to have, let's think about it. It probably comes to rest at position B. So that's going to be spring potential energy, PE little s. Comes to rest by compressing a spring. Yep. So it's at rest, so it has no kinetic energy. Find the spring constant K in terms of G, H. Okay, so this is nice. It's actually asking us to do variables, right? So if it's got potential energy that turns into spring energy, we can set those equal because we're going to assume it's got a conservation of mechanical energy. It's on a frictionless incline, so it's an ideal mechanical system. So potential energy, mgh, is going to equal the spring energy, which is 1/2 kx squared. So we are now trying to solve for k. So k is, let's move the 1/2 to the other side. So k is equal to 2gh. Divide both sides by x squared. So k is equal to 2 times g times h over x squared. That is your answer. Okay, a bunch of experiments to find the effect of things on a pendulum. So here we go. They changed the mass, they changed the length, they changed the angle. I'm going to tell you these are all pretty poorly organized because ideally you only do one change at a time and see what effect that has. Which 3 trials should the student use to test the effect of mass on the period of a pendulum? So let's look at this. Oh my gosh. if you want to affect mass, you want to make sure that other things remain constant. So you want different masses, probably. Oh my gosh, this is a weird question. 310, 215, 210, 310, 310, 310, okay, 25, 215. So the 215 and 215. Here's a 310. R, length 3, angle 10. Length 3, angle 10. Length 3, angle 10. So that gives us 3 trials where the only thing that changes is mass. So trials R, U, and Y. Which 3 trials should the student use to test the effective length on the period of a pendulum? So let's see, we need trials where the mass and the angle are constant. So 210, well, it's not going to be a 1. There's only one trial with mass in there, of 1. Okay. So 2, 3, 3, 3, 2, 2, 3, 2, 210, 215, 215, 215. So there's 3 that have a mass of 3 and an angle of 15. Let's see, 315, 310, 35. So there are not 3 trials that have the same mass and angle. So it's going to have to be a 3, would we say the 3, 210, sorry, the 210, 215, 215, 215. So W, X, and Z. Mass 2, angle 15, 215, 215. The only thing that changes is the length. So W, X, and Z. Okay. A student runs up a flight of stairs in 11 seconds. Let's think about this. It takes 8 seconds to run up the second flight. Determine the power during the 11-second flight climb. Okay, so power is work divided by time, and the work is force times distance. So the force is going to be the object's weight. In this case, 680 newtons is the weight. The distance is the height traveled, so it doesn't matter the angle or anything else. It doesn't matter the horizontal distance, it just matters the height, 3.5 meter stairs in 11.4 seconds. So let's do this. 680 times 3.5 divided by 11.4 gets us 209 watts of power. And one or more sentences. Determine the power, compare the power developed by the student in climbing the stairs in 11.4 seconds to the power developed during the 8.65 trial. I'm not going to write a complete sentence, but you can say it's compared to the 8.65 trial. Well, the student is less powerful if they climb in 11.4 seconds. And I mean, you could even figure that out. You just do 680 times 3.5 divided by 8.5. So the power would be 280 watts if they climb it faster. Instead, they're climbing it more slowly, which means that they are less powerful. Okay. Let's figure out a scale for this. So determine the height of the first hill. Well, let's see. 1, 2, 3, 4, 5, 6, 7. Depending on how particular you want to be. So let's say 7.2 centimeters. And 1 centimeter is 3 meters. On your answer key, this might not actually be exactly the same because the scale that is printed out here might not be what it was originally on Regents questions. 7.2 centimeters. We want to get rid of centimeters. We want to change it to meters. And we know that 1 centimeter is equal to 3 meters. So 7.2 times 3 should give you 21.6. 21.6 meters. Determine the gravitational potential energy at the top of the first hill. So at the top of the first hill, GPE is mgh. And the mass is 650 kilograms. G is 9.8 meters per second squared. And the height is, we said, 21.6 meters. So even if you don't get this, you could just make up a number and still get this question completely correct. 650 times 9.8 times 21.6 is equal to 130. Let's just say 1.38 times 10 to the 5th joules. I mean, you can put the whole number out. It doesn't matter too much. Potential energy. Okay. Equation, substitution with units, answer with the correct units. Last page, here we go. Using one or more complete sentences, compare the kinetic energy at the top of the second hill to kinetic energy at the top of the third hill. Oh, we got to go back for a second. So let's see. So it's going to have energy's conserved, right? We know that it has this much energy. It starts at rest. So the total energy is going to equal 138,000, basically. It's got less energy. It's got the same amount of total energy, but it's got less potential, so it's got more kinetic. So basically, the closer you get to the ground, the less potential it has, but the more kinetic energy it has. So at the bottom, all 138,000 of that is kinetic energy, so it's going to be going the fastest down here. In these loops and dips, for example, it's going pretty fast there. It's a little bit, not quite as fast there, a little bit slower, a little bit slower, a little bit slower, a little bit slower, and it rests there. So at the third hill, it's going slower. I'm sorry. The third hill, it's going faster than the second hill, because at the third hill, it has less potential energy and therefore more kinetic energy, because the total still needs to equal 138,000. Basically saying as it loops and stuff like that. So it's actually going a little faster here than it would at the top of the third hill, but the lower you get, the faster it goes. Because this is a frictionless track. Let's not forget that. So energy is conserved. So we say, compare the kinetic at the top of the second hill to its kinetic energy at the top of the third hill. So at the top of second hill, it has less kinetic energy than at the top of the third hill. Period. Complete sentence. Make that a capital. So it is now grammatically correct. Okay. At the, it has less than at the top of the third hill. Okay. Ooh. This probably involves drawing your own graph. That's always fun. A block is placed on top of a plane. The block slides without friction down the length of the incline. So that means kinetic energy develops as potential energy decreases. So it says determine the gravitational potential energy of the block at the top of the incline. So that's mgh, so 20 kilograms. So let's see, we need to show all calculations. Let's always look at that. PE equals mgh. So PE equals mass of 20 kilograms times G is 9.8 meters per second squared times H is 5 meters. So we don't need that 10 meter thing for anything. So you're looking at about 100, a little bit less than 100. 20 times 9.8 times 5 should be what, 98? Or wait, oh, 980, never mind. 980. I was off by a factor of 10 because I was using 2 kilograms in my head. Okay, perfect. Determine the kinetic energy of the block as it reaches the bottom of the incline. So since there is no friction, basically all that gravitational potential energy should be converted into kinetic energy, so it should also be 980 joules. You sometimes feel like I'm missing something here. It's like, are they trying to trick you? And I don't think so. I don't see anything. Okay. Now, sometimes you might see a question saying, oh, it has 900 joules of kinetic energy. how much internal energy has it developed, or how much heat, or how much work has friction done, and then you just subtract. So if that was 900, started with 980, ended with 900, then the difference would be 80. So it's like, what happened to those 80 joules? Well, it became friction or heat, but this is frictionless. On the axes above, sketch the graph of gravitational potential energy of the block as a function of its kinetic energy for the complete slide. Label your graph with appropriate values and units. So at the top, gravitational potential energy is maximum and kinetic energy is 0, right? At the bottom, kinetic energy is equal to gravitational potential energy at the top, but the GPE is 0. So at the bottom, GPE is 0. At the top, kinetic energy is 0. And as one decreases, the other's got to increase, and they've got to be there's got to be a linear relationship, because GPE is proportional to KE. Now, you might ask yourself, why doesn't it look like this, right? Well, I would be saying as kinetic increases, gravitational increases too. That's not the case. It's really got a negative in there if you want to say the change in one, as one decreases, the other increases. So you get a negative slope to this. But it is just a linear function with a negative slope. I think that's about it. Feel free to ask me questions on anything you got. Hopefully you didn't find any mistakes in these videos, but if you did, please let me know. Thank you very much for watching.